Hello, everyone. This is Professor Ma, and this is the summary on the sections of linear motions. We start out with, we're going to interpret the derivative as rate of change. Rates of change. The rates, of course, refers to ratios, and in general, the ratio of what? Ratio of output versus input. And in mathematical measurements, in application, we usually have a unit for the input and the unit for the output. So let's just use time as the input unit. And output unit could be anything. For example, uh, it could be we're tracking the distance to a bees flying around as time goes on. It could be we're tracking the temperature change as time goes on, the fluctuation of temperature going up and down. Or it could be we measure the change of the weight of a body. Okay. And in this setup, then in particular the rate or the ratios, if we use distance travel, let's suppose this is meters, and then the rates, of course, refers to the change in the distance divided by change in the time. And then its units will be meters per second, for example. And suppose we change in terms of temperature, then we take the ratio of the change in the temperature change versus the time it takes. And this, of course, will be centigrades per hour or per seconds, etc. And the weight gain. And then we take the change in the weight given the amount of time elapsed. And this will be maybe kilogram per year or something like that. Okay. And so we're going to concentrate on the distance one, in particular, the distance of a point moving on a straight line. That's what a linear motion is. And where we have a basic example came from physics. So on Earth, we take something, shoot something up in the air, and then we follow the distance from the ground. D follows this formula. And V is the initial velocity. So in particular, if we shoot the items that's going up as 96 feet per second, then you plug in 96 for the initial V here. In physics, you probably have a V little zero, okay, meaning time zero. And that would be a specific formula for shooting up an object at 96 feet per second from the ground. And from this distance function, we can extract a lot of information about the objects. In particular, we can figure out how long it's going to stay in the air. And from there, we can deduce how long it will take to get to the top. When it's on the ground, the distance is zero. So I solved the equation for zero for t, and I get two answers. Basically, it says, oh, time zero is on the ground, and the time 6 it falls back to on the ground. So from here, I can deduce. It takes 3 seconds to go all the way up, and then the distance you travel in 3 seconds, plug it in, so you travel 144 feet. This will be the maximum height you reach. Okay. Notice that the speed of the stones or the objects changes. We shoot up at 96, but when you reach the top, its speed is zero. Okay. So in other words, at each time there is a different speed, and we will call those instantaneous speed. And to clarify that a little bit, let's first talk about what we mean by average speed. And so we can talk about the average speed, that is how much distance is traveled over a period of time, if A to B. And so that's the delta y over delta t, just a slope. And on the graph, it's the slope of the connecting the 2 points on the distance formula, distance function graph. So for example, from between 1 and 3 seconds, the distance travel was 64 feet in the 2 seconds, so 32 feet per second. between the first and second second, notice, okay. Oh, by the way, that's a slope on the graph for the, if I graph functions, the distance functions. Between the first and second second, okay, and so between here and here, somewhere over there, second over there, and then notice that the slope is steeper. So, and then if I plug it in, yeah, and now it's the average speed in the first to second seconds is 48, and it's faster than between first and third seconds. It's only 32, meaning it's slowing down as it goes up. Okay, and of course, if I let these as I take the average speed closer and closer between 2 points on the graph, that's the definition of the tangent line, and this, therefore, we define this, the slope of the tangent, to be the instantaneous speed or the velocity at time t equal to 8. So, for example, if I take the derivative of these, and so at 1 second, plugging in formulas, we calculate its instantaneous speed at 1 second is 64 feet per second. And so, meaning that if at that instance, the gravitations disappear and the thing floats traveling at the same speed, then it will travel at a fixed constant speed of 64 feet per second along the tangent line. And so here is examples given of distance functions, and we can answer the following questions and easily, okay? And so without calculus derivative, so at time 0, the positions at y equal to 12. So first of all, we have to imagine there's a point going up and down the y-axis. At time 0, it's occupying the position y equal to 12, okay? And think about it, going up or going down. I haven't decided yet, okay? All I know is a snapshot. It's right there. Now, when does it cross point 0? Point 0 is over here. So there's 2 other questions. So at what time, so the point is going up and down, at what time did it cross at the y equal to 0? Or where are south y for y equal to 0? Well, at time t equal to -4, and t equal to 3, okay? So by here, then you will probably say, oh yeah, now I know what's happening, because at time t equal to 4 in the past, it's going upward, okay? And at t somehow, at time t equal to 0, it's passing through this point, okay? But I don't know whether this passing this point is going up or coming down. Well, you have to, let's go up. So let's take it back, and it has to go up because it has to meet first. Okay. Then you have to come down. Maybe have done so. Anyway, all we know is that time t equals 0, y equal to 12. Okay, so actually there are 2 places it has y equal to 12, as we will see. Okay. Now, let's take a look at the velocity. We'll take the derivative and plug in those time, okay? And now we have the velocity at time t equal to -4, at t equal to 0, at t equal to 3, okay? Now, first of all, what does the pluses and minus say? What's the difference between the plus sign and the minus sign? Well, y prime is the rate of change in the y coordinate. Okay, this says basically is 7 to 1 change in the y coordinate, as therefore if I go up 1, y will go up 7. So in other words, these indicate the points going upward. Similarly, negative velocity indicating the point is going downward. Okay. So that's a very important things to realize, the positive and negative signs of the velocity indicated directions you're going. If the axis is horizontal, then positive means the point is going to the right for positive velocity, and the negative for going, oops, I need blue, negative are going to the left, okay? But we are on the y-axis, so positive is going up, negative is going down. In particular, it tells us at derivatives at each point, at this point, it's going up, okay? Because its velocity is 7. And in particular, at the point, at time equal to 0, it's going downward at that point. And it passes through at y equal to 0, then it could keep going downward. So where's the highest value y reached? Well, that's when the velocity is not positive, not going up, nor is going down. So that's a second, so I can, that's what the derivative is 0. I don't have to check second derivative. So that's what the first derivative is 0. And we find out t equal to -1/2. And so from here, I can visualize or think in terms of what the point is doing. The point go from t equal to -4 goes up, and goes up to the high point at 12 1/4, and comes back down at time 0. It crosses the point 12. Then it keeps going. At 30 seconds, it goes through the point 0, and then it keeps going south. And this, of course, is, okay, imagine this actually is the track of the items. And I can also imagine these linear motions described. Is we are projecting a point traveling along this curve on the wall as the shadow of the point. So the point goes up and reach the high points, then goes back down again. Okay, it goes up, and we're watching the shadow. You reach a high point, it comes back down, and so on and so on. And the velocity, the derivative, is the speed of that shadow along that curve. Okay. The second derivative is what we usually terms the acceleration, that is the change in the velocity. And so let's take a look at these examples. And first, let's answer. Okay, now this is on the x-axis, so now it's on the horizontal axis. Okay, and the question asks, when is it the point going to the right, and when is the point going to the left? Remember, that refers to when is x prime positive and when is x prime negative. The velocity is positive. The positive and negative are directions. Okay. And where does it change directions? Okay, and so again, this is basically a sign chart problem. We take the derivatives. So let's go through this problem. Okay, it lists some problem about the second derivative. We will talk about that shortly. So let's look at the with the heading right and heading left. Okay, take the derivatives, draw the sign chart. Here's a sign chart. Okay, so therefore the point is heading to the right after t is bigger than after 1 second. And the point's going to the left for all the time t less than 1 second. Okay, and so in other words, from t equal to -infinity up to the point 1. Okay, and you pause at 0 because the derivative of 0 is 0. Okay, and where does it change direction? Well, that's when you change sign. Okay, and the point is going left. So the point is going left. At that point, beyond that, it's going to go right. So in other words, the curve must have, as in terms of x-axis, if I just draw, the point must be going from here, and at 1 second, okay, it's going left at the t equal to 1 second, and now it starts turning around and doing that and start heading right after 1 second, okay? And if I look at the graph of the distance functions, and if I put it on the x-axis, so here's the point, what's the point doing? The point is coming from t equal to minus infinity and go to x equal to 0 and pause for a second, then continue to the left. Why? Because the sign chart was still negative. Then at t equal to 1, it starts turning around, and the sign chart said the derivative is positive, meaning it's heading toward the right. Okay. How about the second derivatives? Okay, and here's the second derivative, and here's a sign chart of the second derivative. Okay, the second derivative has we had to be a little careful. Usually, we use the word accelerations related to second derivative positive. Okay. So, but second derivative positive does not mean the object is speeding up. The second derivative is positive means the object is being pulled to the right-hand side. Okay. So in particular, if we have the objects, if the velocity is negative, okay, no, if the second derivative is positive, it's pulling the object to the right, okay? If the velocity itself, the velocity, remember, is the first derivative, okay, it's positive, then it's getting pulled to the right even more, so it will speed up, okay? So let me not talk about this one first. Let's talk about second derivative positive, and the first derivative is also positive. So if the object is heading to our right, and the second derivative, the increase, the change in the derivative velocity actually is positive. So it's increasing toward the right. So it's pulling the objects faster toward the right. But if the second derivative is positive, but the first derivative is negative. First derivative is negative means the object is going toward the left. But if the second derivative is positive, means it is pulling the objects toward the right. So in this case, the object actually, the speed is slowing down. Okay, in some sense, this is decelerations. Okay, so again, the word accelerations being second derivative being positive does not mean speeding up, okay? It depends on the directions of the first derivative. Okay, so take that into considerations, and that's all. And that's it. Okay, and so read and do the homeworks on these sections, and bye-bye. And